Understanding the connection between a relation and its inverse is a really foundational component of some of the things that we've really hit in pre-calculus so far, and will really drive a lot of the newer understandings and newer things that we will develop, and is really an overarching theme in terms of the various sorts of parent functions and function families that we examine throughout pre-calculus. So to begin right here, let's explore the idea of what inverses are in context of what you already know and how that will then motivate our discovery and unfolding of new concepts to come. So if we were to consider the operation of addition, what it would mean for us to have inverses in that context is it would mean that under adding of two elements with one another, they would need to basically cancel one another out. So for example, if you were to choose the number 3 to add with some other element in order to try to cancel it out, the other element that you would have to choose would be -3, and the result of that addition would be a sum of 0, of course, right? And so, of course, like another great example could be if you had like -4/7, right? Then you would need to take that number and add it with its opposite of 4/7, and they would cancel out and equal 0, right? If we were to choose like a different operation, so per se multiplication. And again, we want to choose the number 3 to try to cancel out. We would no longer choose -3 like we did before, because the product of 3 and -3 would be -9. So what we actually desire in terms of canceling with multiplication is also not an answer of 0. We actually want the answer to be 1, which is what we call the multiplicative identity element. And so in this case, we'd actually have to multiply 3 with the number 1/3, and then they would cancel out and equal 1. So similarly, using my example of -4/7, -4/7 would need to be multiplied with its reciprocal of -7/4. So both of them would need to be negative because we do want to get a positive one answer. So hence doing the negative times the negative will equal that positive one answer, right? So in doing such a thing, we can say that the numbers that we chose right here, like 3 and -3, they are inverse elements, but specifically we call them additive inverses because they cancel each other out through addition. So whereas when we did like 1/3 and 3, or -4/7 and -7/4, those cancel out but through multiplication. So yes, they're inverses, but this was specific to multiplication. So those there are multiplicative inverses. Okay? Whenever you do cancel out inverses through addition, we always get 0. And that's what we call the identity element in addition. So specifically, it is the additive identity. And then specifically here, these ones are also the identity element, but we call them, or just one, not them, the multiplicative identity element. So the power of the identity elements of 0 and 1 is also that in addition, per se, you could choose any number like 4 and add it with that identity element of 0, and then it just stays 4, right? Or if you took the number 4 and you multiplied it with the multiplicative identity of 1, then the answer just stays 4, right? So just kind of another property that we always see with identity elements. So we want to take those ideas and relationships about inverses and identities and operations and what may have you, and try to put that into a meaningful context of functions and try to see what it would mean to have, say, like a function f and then some other function that would be its inverse, and then also do an operation with those functions that can show that those functions cancel one another out. So what is this mystery operation? What is this mystery other function? And it equals what is the mystery identity element is really what we want to try to be able to answer here today. Okay? So let's have right at it and introduce exactly what it means to have inverse relations, first of all. So what you have listed here is a relation R. So R is equal to, and then because you have these curly braces around everything, that means that you have a set of things, collection of items, and it's going to be a countable or a finite number of collection because that's when we use those curly braces, right? And you'll see that we really have 5 different things within this relation, just a bunch of ordered pairs. And what those ordered pairs really represent is ascending of an x to a y. So for example, since you have the point -6, 2 in that relationship, then -6, 2 is going to be a point on the graph of R. And then we also have half pi, which would be like right there, 0, -5, 4, 4, and -1, 1. Yeah, so those 5 green dots that you see on the graph would be the graph of the relation R. Okay? So we are asked to find the inverse of the relation R. So what an inverse means in context of relations is that we just are going to do a swap, so interchange, same thing, of the input and output elements. So that basically just means that in each correspondence, the x becomes the y and the y becomes the x. So then whatever this inverse of our relationship is, it should consist of these ordered pairs. So 2, -6 should be an ordered pair because you would take that original ordered pair and just swap all the x's and y's. And so then you just do swap all the x's and y's for all of these, and the last one we'll get is 1, -1, right? So if I were to plot all 5 of these ordered pairs, so first of all 2, -6, and then pi half, -5, 0, and 4, 4 is actually going to stay the same, and 1, -1 now, we get these blue ordered pairs, okay? So whenever we look at graphs of inverse relations, there's one foundational characteristic that always holds in graphs of inverses, and that would be some beautiful symmetry that occurs in these graphs. You'll realize and recognize here that the line y equals x happens to be the line of symmetry for the graphs of any inverse relations. So you can see that, for example, this point right here maps perpendicularly across that line of symmetry, same distance to this corresponding point over here. And that holds true for all of the other points. So then, of course, that point that's right on the line of symmetry stays right there, right? So another way that you can see this besides just seeing a collection of ordered pairs is if you're given some sort of an equation with 2 different variables, and that one you have y and x, and then you were asked to find an equation for the inverse of the relation. Similarly, we want to interchange the inputs and output elements, right? So here we can just swap the x and y's around. So you make the y become an x, and then all of the x's become y's. And so this right here would end up being the equation for the inverse of the relation. Okay? Well, the graph right there is just showing you what the graph of one of the equations would look like and what the other one would look like in the inverse. So this red graph right here is actually the equation of that. So it matches up to that equation right there. And it just illustrates the fact, again, that because they're inverses, they're going to have a nice little bit of symmetry across y equals x. Okay? So just formalizing that idea about inverse relations, you can say that a relation R's inverse relation, and that's what we're defining right here. And what we'll use symbolically to represent that is we'll denote it as this. So there's a little -1 up there in the superscript part. It's not an exponent. Okay. So the way that you read that is you read this as R inverse. So it just means what the inverse relation of R is. Okay. So a relation R's inverse relation, denoted as R inverse, is the relation that you form by just swapping input and outputs from the original relation R. Okay, so you just switch all of the x's and y's from each of the corresponding pairs. Okay. So what that does mean then, as kind of a consequence, is that then the domain of the original relation R will always be equivalent to the range of R inverse. And then we also will know that the range of the original relation R will be equal to the domain of this inverse relation. Pretty easy to understand because you're just swapping x's and y's, right? All right, so you'll see on here, there's a couple examples of different relations between quantities. So the one thing that I want to draw your attention to first here is that this Dunkin' Donuts menu and then the mapping diagram, they are currently functions, both of them are. And what that means is if they are functions, is that each input maps to exactly one output, right? And you'll see that that holds true that every type of drink goes to just one price. It's not going to have two different prices. That would be weird and unfair to the customer, right? And then the same thing is also holding true currently there as well. What we want to consider here is whether or not the inverse relations, all of these relations that are given, are also functions. So then we would then need to consider, okay, what if we send everything backwards, right? We send all the outputs back to the inputs. So now this price of $5.11 is going to send this way, and this gets sent this way, etc., right? For the Dunkin' Donuts menu, it would cause a little bit of a problem because you'll see that then there are a couple of different menu items that do have the same price of $6.11. So then in the inverse relation, where now 611 is now considered an input, 611 would be being sent to the iced latte, and then it's also being sent to the iced cappuccino, which then makes that inverse relation not a function. So here, the inverse is not a function, right? Then if you look at the mapping diagram, and you send everything backwards now instead, because all of these numbers here are all different from one another, you won't have any repeated new x's in this inverse relationship. So therefore, the backwards version of this is going to be a function as well, right? So here we can see that the inverse is indeed a function. In the last example, you had just seen that there was a function whose inverse was also a function when -3 had mapped to -27, etc. So it turns out that in those sorts of relations where both the original and the inverse are both functions, that we can call them one-to-one functions. Now, there can be relations that are only one-to-one, but then that original relation might not be a function. So what I'm going to put as a definition for right here is going to be just a definition for what it means for a relation to be one-to-one, And then we can extend that to call a function one-to-one if it's originally a function that is one-to-one, right? So we can say that a relation doesn't necessarily have to be a function, but a relation R is going to be 1-to-1 if for every possible two different x numbers we could pick that belong to the domain of that relation R, that if the y value at A and the y value at B are equal, then actually A and B are equal to one another and can't actually be different from each other. So basically all that that's saying then is if you have some certain y value that the relation obtains, then actually there can only be one x that goes to any particular y value. So each y is only corresponding to one x in looser terms, right? So each y value just corresponds to just one x. And then one thing that I should adjust about what I wrote right here is the fact that I wrote f of, but I never called anything f. What I should have said is r of a and r of b, so that's how it was a relation. Okay? So then if you knew that relation R was actually a function to begin with that had this one-to-one property, then you call it a one-to-one function. All right, so we really want to play around with this idea of being one-to-one and talk about it symbolically with equations and graphs and other things to come, and it'll settle in really nicely for you here. So the first thing I want to do with this one-to-one idea is to do this proof that f of x equals 5x minus 7 is 1-to-1. So this is going to use that definition that we just saw, that if we knew that f of a equals f of b, right, then we want to try to show that a and b are actually the same things. So what I want to try to do then is I want to try to just let a and b be in the domain of our function f right here. And then I'm going to assume that f of a equals f of b. So at this point, this is not part of my proof, but now what I want to try to do is I want to show that a is equal to b somehow, just using this information that's given. So based on my assumption, f of a and f of b would be two quantities that we know what they are, because you would just plug in a into f, so 5a minus 7, and plug b into f, so 5b minus 7. Those things would then be equal, so we can say that that is true because we know that f of x is equal to 5 times the x minus 7, right? And then I could take that equation that I have of 5a minus 7 and 5b minus 7 equaling one another, and we'll be able to find a way to show that a and b are equal to the same thing. So then if I just add 7 to both sides, then we'll have that 5a and 5b are equal to one another. And multiplying by 1/5 to both sides then we'll have that a and b are equal to one another. And that's what we desire to show. So what that really shows us then is that for this particular function, that each y value on that graph of the function has only one x corresponding to that particular y. So you won't have multiple different x's going to any y value. And if you think about visually why that is, we know that f of x equals 5x minus 7 is a linear function because it's an mx plus b form. So we know the y-intercept is going to be at -7. It's got a positive 5 slope. So this is going to be the graph of that. And for whatever point you pick, so like if you pick this point right here, and it has, say, this y value right here, there's only one x that ever has that y value, because there's no other places on the graph to the left or to the right of that point that has the same y value. So you wouldn't be able to find another x that ever goes to that y value. So it's only just that one x, right? So that's the idea of what it means to be one-to-one, and this line that I just drew right here is a really important aspect of one-to-one functions that we'll address in a little while. Okay? So here, we kind of want to do an opposite thing in terms of proving that g of x equals the quantity of x plus 4 squared, and then minus 9. It's not one-to-one. So what that would mean if it was not one-to-one would mean that if we find that f of a equals f of b, so we've got some y values, right? Then actually a and b would not necessarily have to equal one another. So we would be able to actually find two different x values that we could plug in that could give us the same y value, I guess. So one way we could try to actually justify that is just by trying to plug in some numbers to see if we can get the same y values. And in fact, maybe if we let like x be, say, 3, how about? Then that would imply that g of 3 would be equal to 3 plus 4 squared minus 9. 3 plus 4 is 7, and 7 squared is 49. 49 minus 9 is 40. So we get a y value of 40, right? But also, if we had like maybe x equals negative 11, then g of negative 11 would be equal to negative 11 plus 4 squared minus 9. And negative 11 plus 4 is negative 7, but 1 squared gives us a positive 49, and then subtract 9 gives us 40 again. So right there, now we've actually basically proven that it's not one-to-one, because for the same y value, right, we have that g of 3 is equal to g of negative 11, right, because they both equal 40, but definitely 3 and negative 11 are not equal to each other. So therefore, it can't be a one-to-one function. Okay. So you'll see here that graphically there's a couple of different functions. So maybe we'll just call this red one here f, and then this blue one here g. So it turns out that the graph of f, this is something that is not 1 to 1 at all. Definitely not one-to-one. And the reason why that is because like right here are two different points where the y values of them are 3, but the x values are different of negative 7 as well as negative 1. So it can't be one-to-one. And ultimately, why that is because when you look horizontally, right, you've got that horizontal line that crosses the graph at multiple points, which then means that you have the same y values but different x's, right? So it can't be one-to-one. But this other graph of g right here, this is a 1-to-1 relation, because for each y value that you have, so like right here, when you have a y of negative 1, there's no other x's that ever have a y value of negative 1. And that's because, really, any horizontal line is only ever going to cross the graph once, right? Never more than once. You should realize, too, that this relation is actually not a function, because to be a function means it would have to pass the vertical line test, but it doesn't because it hits two different points on the graph. So that's actually not a function, but at least this is a relation that is one-to-one, right? So it's this idea of the horizontal line test that can inform your understanding of one-to-oneness in graphs of functions. So you could say that a function, not necessarily functions, you can say that a relation is 1-to-1 if every possible horizontal line hits the graph of the relation at most once, so never more. Might not hit it. Some certain horizontal lines might never hit the graph, which is okay. You just never want it to hit the graph twice or more. So here we're asked to determine whether each function is one-to-one, and thus would also have an inverse that is also a function. And we'll talk about that aspect in a little while. So mostly I just want us to understand at this point in time whether each of these is a one-to-one relation. So you'll see that for this graph right here, this is the horizontal line test. So therefore this is a one-to-one relation, and is actually a one-to-one function, because the original of this also passed the vertical line test as well. So actually all of these to start with are all functions currently, because they all pass the vertical line test, right? You'll see that for the second example that it hits the graph once right there, but then like right there it hits the graph at 3 different points, which is not okay to be one-to-one, I guess. So this right here is not a one-to-one relation because of that. And then this last one right here, it only is ever going to hit once if you draw a horizontal line. So that one would be one-to-one as well. The first one. And just a couple more graphs right here. So right here, it's only ever going to hit the graph once. So it does, start to flatten out kind of right there, but the graph never goes perfectly flat, so any horizontal line will actually hit the graph just exactly once. Right on the x-axis, there's actually no point on the graph, so it hits nothing there. And then again down here, it's only ever going to hit once. So this is definitely a one-to-one relation. And then for the last one, never hits, never hits, never hits, never hits. Oh, there it hits one, right? Doesn't hit anything, but then it does hit two right there, which is not okay. So this is not going to be a one-to-one, because there we had 2 points that had y values of -1, but x's of 1 and -1 that we get, so it can't be one-to-one. Okay? All right. So then what it means then, really, really, really truly, for us to have inverse functions is we need it to be a function originally, and then we also need it to be one-to-one. So we can say that a function f, meaning that we already have a function to begin with, has an inverse that is also a function if f, the original function, is 1-to-1. And then can call the inverse relation of f inverse, an inverse function, because then we'll actually know that that inverse relation will actually be an inverse function. Putting this into more simple terms, it really just means that you need f to pass the vertical line test in order for the original thing to be a function, and then you need the inverse relation to then also pass the vertical line test, and then you can call that inverse also a function. But in order for this condition right here to hold, for the inverse to pass the vertical line test, that is equivalent to the fact that f is going to pass the horizontal line test. Because what happens in the graphs of relation and its inverse is they're kind of like flips, how they flip over the y equals x. And so that's why that needs to hold. And so then similarly, when f passes the vertical line test, that's equivalent to the inverse actually passing the horizontal line test as well. Okay? So the only way that you can actually have inverse functions is when in both the original and the inverse, the graphs in both situations pass both the vertical line test and the horizontal line test. Okay? So how that plays out then right here is you could say that if this graph is called f, and this is g, and this is h, and this is j, let's say, right? You can see that it fails the vertical line test. So f is not a function. And then when you look at the horizontal lines, it does pass the horizontal line test. So you'd be able to say that f inverse is a function, right? So the only time, right, that you can actually have an inverse function is if the original passes the horizontal line test, and then the inverse will be a function, right? And then here, you can see that it passes the vertical line test, so you can see that g is a function, but then it fails the horizontal line test. So then g inverse is not going to be a function because of that, right? And then for this graph, it passes the vertical line test, and it also passes the horizontal line test. So h is a function, and then also h inverse is a function, right? And then for the last one, it fails the vertical, and it fails the horizontal. So that means that this original relation j is not a function at all. And then also the inverse of this relationship is not going to be a function either. Okay. So the only ways where you got the inverse to be a function was in these two cases, and that was when actually, in all reality, the horizontal line test was passed, right? Because if the horizontal line test gets passed in a function, then when you find the inverse's vertical line test will get passed, and then it will be a function. Okay. So we want to transition now into some more symbolic equation context of being able to find inverses for various different equations. So we are asked here to determine whether the given function is invertible, and then if so, find an equation of the inverse of the given function. So we're going to talk about this a little bit more formally towards the end here. What it means to be invertible is it means that you can actually find an inverse of a function that is also a function. Okay, so invertible means that both the original and the inverse are both actual functions past the vertical line test when you graph both of them. So that means then the original would have to pass the vertical and the horizontal, right? So here you have f of x equals 2x minus 8. That's a line, right? So when you graph it, starts at negative 8 and then goes at a slope of 2. So it's going to look like this. So voila, there's the original graph f, right? So you'll see that because f does also pass the horizontal line test, in addition to passing the vertical line test to be a function, that then f does have an inverse that's also a function. So therefore the function here is invertible. So what we want to try to do then is then find the inverse equation for the function. So the way that you can find the inverse is by just swapping the variables. So the inverse equation is going to be x equals 2y minus 8 by switching x and y around. And then what you'll just need to do from there is just solve for this new y alone and get an equation. So just like get this guy right here alone. So you have to undo the fact that that y is being multiplied by 2, and then you're also subtracting 8. So in order, undo the subtracting 8 first. So add 8 to both sides, and you get x plus 8 is equal to 2 times y. And then you can divide both sides by 2, or both sides by half, same thing. But so the half to distribute to the x and to the 8. So half x plus 4 equals y. I'll label it like this, because this right here would actually be the inverse function using the same notation. So f inverse of x. If we were to graph that inverse, so this right here, you'd now have a y-intercept at 4, and then a slope of 1/2, and so then your graph is going to end up looking like this. Okay? And you'll see then that because we've graphed the inverses, that indeed y equals x is going to be the line of symmetry for the blue and red graphs, just like inverses always reflect over y equals x. Okay. So we're asking ourselves the same thing right here to try to find the inverse equation. Okay, so what we have is we have y equals x to the third plus 2. So if you had x to the third, you know that these points right here would be some key points on x to the third, because 2 to the third is 8, 1 to the third is 1, 0 to the third is 0, negative 1 to the third is negative 1, negative 2 to the third is negative 8, right? So the plus 2 just shifts everything up 2 units. So if you shift all of those points up 2 units, you get these points right here. So this would give us the graph of g then. You'll see that it does pass the horizontal line test in addition to the vertical line test. So g is going to be invertible. So to get the equation then for the inverse, you'd have to switch the x and y's around and then solve. So to solve this for y, you'll want to try to get the y to the third alone first, and then you'll have to undo the cubing of it as well after you've gotten the y to the third alone. So subtract 2 from both sides first, you'll get this. And then you can just do like a cube root to both sides to get rid of that exponent of 3. So then the cube root of the quantity x minus 2 is going to equal g inverse of x. Okay. And so if we were to graph this equation here, this would be like graphing the cube root function. But then because you're subtracting 2 from x inside, it should shift the graph to the right 2 units. So normally when you have a cube root function, you'd have kind of these key points on there, because the cube root of 8 is 2, the cube root of 1 is 1, etc., right? So if you just take all of those points and you shift them to the right 2 units, look at this. For the graph of g inverse, and then upon visual inspection, you'll see that they do satisfy that. Y equals x, line symmetry, okay? So here we have y equals x squared minus 1, which would be a parabola, but just shifted down by 1, right? So when you graph y equals x squared minus 1, you would have sort of this sort of thing going on. And then you'll notice that that actually fails the horizontal line test, which then means that its inverse would not be a function. So you could find an inverse. When you graph the inverse, it's going to end up kind of looking something like this. But then that blue graph fails the vertical line test, so the blue graph can't be a function, right? So therefore, we can't actually find an inverse that is also a function, right? So because h is not invertible, then we wouldn't be able to so h inverse doesn't exist if we're assuming that h inverse is going to be a function. Okay, you can still find an equation for h inverse, but then it's not going to result in actual functions. So if you were to do so, you'd have to set x equal to y squared minus 1, x plus 1 equals y squared by adding 1 to both sides. But it's then the fact that when you do an even root to both sides that you get both plus minus. And the fact that you get both plus minus then means that you get the positive square root graph and then also the negative square root graph. And having both of them means that you're going to fail the vertical line test. Not good then. Okay. But if we were to have like another parabola, like this one, so this one would be 1/3 x squared plus 2, it's shifted up by 2, and then it's just a little bit wider. So I'm not going to be super picky right now. I'm just going to sketch it out. Okay, it's going to look something like that, right? But we also have this additional restriction that x can only be greater than or equal to 0. So that would mean then that we really only have that graph, because that corresponds to x values being positive or 0, right? Well, now that we have this, now this graph actually does pass the horizontal line test. If we had the other half of the parabola, it wouldn't, because then you'd be hitting 2 points, right? So now we can actually find an inverse for this. And so when we solve, and we have now x equals 1/3 y squared plus 2, solve for y, so subtract 2 first, we get x minus 2 equals 1/3 y squared. And then multiply by 3, and you have 3x minus 6 equals y squared. And then take the square root of both sides, you're going to get both plus minus the square root of 3x minus 6 equals y then. But that would mean then you would have something that's not a function because you have both of the square roots. So because you had x was greater than or equal to 0, you're going to want to only take the positive root in this case. So then just j inverse of x should equal just the positive root of 3x minus 6 then. So what that then means is because you had this domain restriction where x was greater than or equal to y, you also have to switch and make the y now replace the x. So then you would have that y is greater than or equal to 0 as part of your equation for j inverse. And when you do actually graph this, you're going to get something that looks something like this, where indeed on that graph the y values are all greater than or equal to 0. Because if you had the other half of this, it would look like this, but then those y values would be negative, which would not work, right? So there we have that. Okay, same idea would kind of persist through here. We don't need to talk through this. I'll post this on the notes so you can see, but there's nothing new happening there. All right, so just some other examples of being able to find some inverse equations for different sorts of functions. That's all that it says. Find an equation for the inverse function of each function. So now I'm actually kind of guaranteeing with all these examples that we would be able to find an actual inverse equation for all of these different ones. So for the first one, we have r of x, where x is greater than or equal to 5/3. That restriction is really important for when we find the inverse. So then to get the inverse equation, we'll set x equal to the square root of 3y minus 5, and then solve. So first you'll need to get rid of the square root, which you can square both sides. And then you get x squared is equal to 3y minus 5. Add 5 to both sides. X squared plus 5 is going to equal just 3y now. And then divide everything by 3. So 1/3 x squared plus 5/3 will equal r inverse of x. Because you have this domain restriction right here in the original function for r as well, that means that now switch the variable to y greater than or equal to 5/3 is going to be part of that as well. So there you have that. Okay. These couple examples just are here so you kind of see the similarities and differences in terms of solving for equations that look pretty similar. So in the first one right here, when you first of all get the inverse equation where x is equal to the 5th root of -4 y to the 3rd, everything there is under the 5th root. So your first step would be to cancel out the 5th root and then exponentiate both sides by raising it to the power of 5. And then x to the 5th is going to equal -4 y to the 3rd. Versus in the other problem over here, if we were to set up by switching the variables, first of all, we would have this. But now, the y is cubed and then 5th rooted and then multiplied by -4, so you'd actually want to divide by -4 to both sides, which multiplied by -1/4 is the same. So then you'd result in -1/4 x is equal to 5th root of y to the 3rd. So just a little bit of order, different order of solving stuff, right? So going back to this equation right here, now you'd want to divide by the -4. So then you get -1/4 x to the 5th on this side equals y to the 3rd. And then you can cube root both sides. So the cube root of -1/4 x to the 5th is going to equal y. Or I guess we could say that is s inverse of x. And then for the other one, okay, raised to the fifth power, because everything is under the fifth root there. When you do that, I guess, you could really do negative 1/4 times negative 1/4 times negative 1/4 5 times. You end up getting a negative, because you multiply a negative an odd number of times, 5 times, right? 4 times 4 times 4 times 4 times 4, 5 times is 24. So you get that, and x to the fifth is going to equal y to the third. And then you can cube roots to get the y alone. So the cube root of negative 1 over 1024 x to the fifth is going to be equal to g inverse of x. Excellent. Some other just sort of solving ones to consider here. So with this one, if we were going to try to find an inverse function, actually I should have put a domain restriction on this one. It does need that because if you had a quartic, it would fail the horizontal line test. So let's suppose that x was less than or equal to 0, then it would actually be 1 to 1. So then we can say that x is going to be equal to 1/2, y to the fourth now, and then also put in this restriction where y is going to need to be negative. So before you can fourth root both sides, you're going to have to get rid of the 1/2. So multiply both sides by 2. And then you can fourth root both sides. Because you're doing an even root there, you're going to get both plus and minus. So the plus minus fourth root of 2x is going to be equal to y. Y is less than or equal to 0. Because of this restriction, though, that we want y to be less than or equal to 0, we would actually want to take the negative root. So u inverse of x should be equal to the negative fourth root of 2x then, and then we'd have that restriction that y is less than or equal to 0 in there still as well. Wonderful. When you're solving this one, because it has the fifth root, you don't get plus or minus, so then you don't have to worry about that. And actually, for any odd roots, you don't have to worry about that ever at all. So it's just because if it's an odd function, it's going to be like invertible in functions like this. So nothing super fancy other than just make sure you solve it correctly, I guess, to find the inverse of this. So switch the x and y's around. What you'll want to try to do is try to get this here alone so you can fifth root it. So you got to get rid of the 10 as well as the subtracting or the negative that's really multiplying. So subtract 10 from both sides, then x minus 10 is going to be equal to negative of the y minus 2 to the fifth. And then if you divide both sides by a negative 1, then you get negative x plus 10. Both of those signs are going to change, equals y minus 2 to the fifth. Then you can fifth root both sides to get y minus 2 alone, and then add 2. So the fifth root of negative x plus 10, and then plus 2 is going to equal w inverse of x. And the last one that you see on this slide, at least, for the inverse, x would equal 8y to the 3/2. So you can multiply both sides by 8 first, so you get y to the 3/2, which is going to equal x over 8, or 1/8 of x. And then you'll want to raise both sides to the 2/3 power. The reason why you do that is because then these exponents right here multiply with one another to equal 6 over 6, or 1. So it becomes y to the 1 power, or just, in other words, y on that side, equals. You'll have x to the 2/3 on top and 8 to the 2/3 on bottom. But since 8 to the 2/3 is equivalent to the cube root of, because the 3 is the bottom number of that exponent, and 8 and then squared, where we know the cube root of 8 is 2 and 2 squared is 4, we could just say, oh, it's just x to the 2/3 over 4 equals the inverse of x, right? And then some fractiony sorts of examples where you have like an x on the bottom is important to be able to solve in terms of finding inverse equations. So for this right here, to get the inverse, you'll set x equal to 4 over y plus 2, and then need to solve for y. Because y is on the bottom with the plus 2, I would multiply this side of the equation by y plus 2, and then of course do the same. You'll need to make sure that the y plus 2 is in parentheses, so you're multiplying by the entire quantity. So you'll get then y plus 2 in parentheses multiplying with x is going to equal just 4 now, because the y plus 2 is canceled out. Then I wouldn't distribute the x in a case like this, because what you could do now is just undo that multiplication by x by dividing by x, and then dividing by x on the other side, which would give you now only y plus 2 alone equals 4 divided by x, and then you just subtract 2 to get the y alone. So d inverse of x will equal 4 over x minus 2 then. Okay, so it's not too bad. And then for C, it'll look like this once you interchange the variables. And then, yeah, I would multiply both sides by that cube root of 3y. And that cancels all of that out, so you get just a 9 on this side is going to equal cube root of 3y times x. And then, yeah, I would divide by x. So now the cube root of 3y is equal to 9 divided by x. Then you're going to get the cube root undone, so raise both sides to an exponent of 3. And then now just 3y is going to equal, so when you do this part right here of 9 over x cubed, you'll do 9 over x times 9 over x times 9 over x. So 9 times 9 times 9 ends up being this number, 729. X times x times x ends up being x to the third. And then you can multiply both sides by 1/3. So you have just the y alone, and then that means that y is going to equal, it turns out 729 divided by 3 is 243. So 243 over x to the third. So that is going to give you the equation for C inverse then. So along the idea of inverses is we want to be able to understand the relationships between functions that are inverses of one another. So harkening way back to the beginning of all of this, we can show that 6 and -6 are inverses because if you add them, right, they cancel one another out. So we've done so, right? And we can also verify that these two numbers are inverses, but if you add them, they're not going to cancel out, right? But if you multiply them, -4/3 and multiply with -3/4 equals 12 over 12, which equals 1. So therefore, they're inverses. So specifically, we were doing additive inverses here, and then here we were doing multiplicative inverses here, right? So what does that look like if we're trying to do this with functions, right? So we want to try to prove that f and g are actually inverses of one another. We don't want to add them together. We don't want to multiply them together either. So what we know is true with inverses is that for a function f, if it sends some input element, say m, to an output element n, then because g would be the inverse, it should send an input element of n to an output element of n, right? Because you swap the x and y variables. So what we could try to then show to show that these are inverses is that if you take, say, g, and you plug in some element, say, c, into it, and we know that it equals d, that would mean, of course, that f of d would equal c, right? But then if we were to do g of c, which we know is d, and put that into f, that would be equivalent to f of d, because we know that g of c is equal to d, but f of d is equal to c, which would equal c, which then means that this element that we plugged into g first, and then that g of c got plugged into f, just resulted in c. That would actually just verify that the functions are canceling one another out. And so function composition, plugging functions into functions, can actually verify that things are inverses. So what I can do then is I can do f of g of whatever input element I want, so maybe like z. And if I can show that that equals z, then you showed that they're inverses. Okay, so let's go ahead and do that. So if I was going to do f of g of z, that would be doing f of g of z, or just basically doing f of 1/4 x minus 9/4, or 1/4 z minus 9/4 if we're using the variable z, I guess. So it's just a matter of plugging in 1/4 z minus 9/4 into the function f, 4x. So now we would have 4 times blank plus 9, where we're going to plug in g in for that variable into this. And then if you distribute the 4, you get 1z. And 4 times that ends up being -9, because the 4 on top and bottom cancel. And then plus 9 after all of that, which equals z. So therefore, that verifies that they're inverses. Okay. You can go backwards as well. So if you wanted to do g of f of z, and basically that would just be putting f into g. So doing the 1/4 x minus 9/4, but instead then you put the 4z plus 9 in right here. Let's distribute the 1/4, and then you'd get z, and 1/4 of that would be plus 9/4, and you got the minus 9/4 after that, and that equals z. Okay, so it's going to work the other way as well. So you just need to show it one of the ways, and then that's sufficient to know that they're going to be inverse functions of one another. Okay. So this idea about inverse functions and function compositions just says that if f and g are inverse functions, then plugging x into g and then g of x into f should equal x, which is also equal to plugging x into f and plugging f of x into g. Yeah. So then, of course, that means that g is equal to f inverse then, or f is equal to g inverse, right? So you could do a similar sort of thing right here in terms of proving that these guys are going to be inverses. There's just a little bit of algebra right here. So if you want to prove that they're inverses, plug one of them into the other. So maybe you'd want to take this right here and plug it in, but it's going to have to plug in right there and then also plug in right there. So when we're plugging it into k, that means that h of x is getting plugged into k. And so then you would get 4 input plus 6 over 3 input minus 1. X plus 6 over 3x minus 4 and right there. And x plus 6 over 3x minus 4 right there. It's got a lot of fractiony sort of stuff, right? So what we might try to consider right here is just trying to get all of this stuff right here written as one single fraction. So when you have the 4 multiplied to this fraction, you're going to get a numerator of 4x plus 24 over the 3x minus 4. But then with this 6, you would probably want to multiply it by that same 3x minus 4. So you get a common denominator, and then have 18x minus 24 over 3x minus 4. And then you'd be able to add those fractions together, and then just get a 4x plus 18x, so 22x, plus 24 minus 24 cancels, and then just over 3x minus 4 there. And then just do a similar thing with the denominator right here. If you multiply the 3, you get 3x plus 18 over the 3x minus 4. But then just take this -1 right here, multiply by 3x minus 4 over 3x minus 4. Subtract 3x minus 4 over 3x minus 4. And then that's going to be equal to 3x minus 3x will cancel, and 18 minus -4 will equal 22 over 3x minus 4. And then now you can actually just take this and do keep, change to multiply, and flip. And then you'll find that the 3x minus 4s will cancel, and the 22s will cancel, and it just equals x. You can see right there. So therefore, you know that they're inverses. And then similarly right here, you can go either way in terms of proving that these are inverses, m and n. So perhaps you could take this guy right here and plug it in for x into the other one. So then you would have that n of m of x would equal the cube of the cube root of x plus 12 minus 12. And then cubing a cube root would do that. It's 12 minus 12, which equals x, right? And then you can go the other way too, where you could take the x cubed minus 12 and plug it in for x underneath that cube root. So m of n of x would be equal to the cube root of whatever plus 12, where you plug in the x cubed minus 12, which would then negative 12 plus 12 cancels, so it's just cube root of x to the third, but that just equals x. Okay, it verifies that you have inverses there as well. And then the last idea to bring everything all together is the idea of invertibility of functions and what it means for functions to be invertible. So you can say that f is an invertible function if both f and f inverse are functions. So in simpler terms, it just means that you can find that f is going to pass vertical line tests and horizontal line tests both. So it's got to be both a function to pass the vertical line test, and then also be 1-to-1 to pass the horizontal line test. Okay, so as long as you find something that's both a function and a 1-to-1, it's going to be invertible, and then both the original and the inverse are both functions. Okay. So here we're asked to determine whether each function is invertible. So this function right here, well, you can see it as a function because each input goes to one output. If we were to invert it, we'd want to make sure that it's also 1-to-1. But you'll see that this output value actually corresponds to two different x's. And so then in the backwards version of this, when we send x to a and then we send y to both b and c, then the inverse would not be a function. So that means that this right here is not invertible. The specific reason why is that this was not 1-to-1. Okay, so it's got to be both function and 1-to-1 to be invertible. For this one, it is a function to begin with, which is good. And then each y also has just one x going to it. So therefore, this is definitely going to be an invertible function because it is both a function to begin with, and then it's also 1-to-1, which just simply means that the inverse of this is also going to be a function. Okay. Graphically, if something's invertible, it's got to be both a function and 1-to-1. So it's just got to pass both the horizontal and the vertical line test. So here, passes the vertical line test, passes the horizontal line test. So therefore, it is invertible because it passes both of those tests, right? This one here is a function because it passes the vertical line test. However, it fails the horizontal line test. So therefore, it cannot be invertible. So its inverse would not be a function. So it is not invertible. And then finally, from equations, you want to know if something's invertible, then you can kind of think about it graphically, right? This thing is a parabola. It's a vertical parabola. And it's got a +1 coefficient for x squared, so it's a happy parabola. Well, that means it's going to fail the horizontal line test, which means it's not 1. So no. So no, this is not invertible. So its inverse equation will not be a function, right? Well, that's the same thing. But now we've said that x is greater than -1. Well, what does -1 mean? Well, it's actually at the axis of symmetry, because the axis of symmetry for a parabola should be -b over 2a, which is -1. So if we graph the parabola only to the right side of -1, then it'll pass the horizontal line test, right? So we'd be able to find an inverse. So this is definitely going to be invertible because it's a function and it is also 1-to-1, right? So for this very last one, I just want to take a little bit of time and show you how to find the inverse equation. It's pretty slick and a pretty cool way to be able to do so. So to get the inverse equation for f inverse, you would set x equal to y squared plus 2y minus 1, right? And then you would also have y is greater than negative 1 by switching that there. So you kind of have a little bit of an issue right here because you have y's in separate terms. But one thing that you could do here is you could have it so that you have y squared plus 2y and then try to complete the square. So half of the 2 is 1 and 1 squared is 1. So if you had this expression right here, plus 1, that would be great. But now since I just randomly plus this 1 to the equation, I'm going to also subtract 1 to undo that. And then this subtracting 1 should still be there as well. So if you look at all of the term, 1, 2, 3, 4, 5 right here, if you were to simplify it by like canceling these two out, your equation would still be y squared plus 2y minus 1 overall. So the equation hasn't changed. But then by writing it like this, you can easily see how this part that's in the parentheses right here will be able to be written as y plus 1 squared, because we completed the square right there. And then those two numbers, if we combine them, becomes minus 2. So x equals that. And then we can solve this where we get literally just one y alone. So x plus 2, first of all, is going to equal y plus 1 squared. And we can just solve by the square root property. So square root this side and square root this side. So the square root of x plus 2 is equal to y plus 1. Now, technically, you get both plus and minus right there, since we're solving by the square root property. Because we want y to be greater than negative 1, we want positive y's, we'll want to take the positive square root. So just the positive square root then is equal to y plus 1. And then if you get the y alone by subtracting 1 from both sides, then f inverse of x equal the positive square root of x plus 2, and then subtract 1 for the inverse equation.